we want to look at this quadratic function and see what its graph looks like. In the previous video, we looked at the graph of just kind of a standard quadratic function, f of x equals x squared. That's a parabola that would have its vertex, that's the turning point, would have its vertex at the origin and would open up. It opens up because the coefficient of that squared term is positive 1. When we graph the quadratic function such as this, f of x equals x squared plus 6x plus 9, the parabola is going to be moved around. It's going to be moved around potentially both horizontally and vertically. And so we need to see what that parabola would look like. And we can learn a lot about what that parabola looks like by finding some key information. And the first piece of key information we want to find from the equation is the vertex of the parabola. The vertex is, again, that turning point. It's where the parabola comes down, turns, and starts back up. That's the vertex. Well, the vertex, again, is just a point, so it's an ordered pair. And the x value of the vertex can be found by finding minus b over 2a, where b refers to the coefficient of the first power term, and a refers to the coefficient of the squared term. So if we find that x value, if we then evaluate the function at whatever that value is, we will know the y value of the vertex. So our first chore is to find that minus b over 2a point. So in this case, that's going to be negative 6. Again, the b is the coefficient of the first power term, over 2 times 1. The coefficient of the second power term there is 1. So that's negative 6 over 2. That's negative 3. So the x value of the vertex is negative 3. Now, let's evaluate that function at negative 3 to see what the y value of the vertex would be. So that's going to be the square of negative 3 plus 6 times negative 3 plus 9. The square of negative 3 is going to be 9, plus 6 times negative 3 is negative 18, plus 9. Well, 9 and 9 is 18. 18 minus 18 is 0. So the vertex that we have for this particular quadratic function would be the point negative 3 for x, 0 for y. So the vertex is going to be negative 3, 0. And again, the way we find the vertex, you find the vertex by first finding negative b over 2a and then evaluating the function at that point. So here the vertex is negative 3, 0. I know this parabola opens up because the squared term's coefficient is positive. Well, also, if you recall, the original standard quadratic function, f of x equals x squared, is symmetric with respect to the y-axis. Well, of course, this parabola is not going to be symmetric with respect to the y-axis because it's been moved off of the y-axis. Its turning point, its vertex, is now here at negative 3, 0. But it still exhibits symmetry. It exhibits symmetry with respect to this vertical line. And that vertical line is sometimes called the axis of symmetry. And in this particular instance, the axis of symmetry for this parabola is the vertical line x equals negative 3. So for every point that's on this side of the line, there will be a symmetric point on this side of the line. Well, let's find a couple of points on one side of the line. We'll get their symmetric points on the other side, and we will have our graph of this quadratic function. Well, one of the points that we could find would be the y-intercept. That'd be a very easy point to find. Remember, to find the y-intercept, we let x be 0. So if I let x be 0, those two terms become 0, and the y-intercept would be the point 0, 9. And again, the way we find the y-intercept is by letting x be 0 in the function. So the y-intercept is the point 0, 9, which is here. Well, then that means that there is a point symmetric to this point over here on the other side of this axis of symmetry. And the way we find that is we ask ourselves, how many x values did we go to the right to find this point? And we went 1, 2, 3 x values to the right. So if we go 3 x values to the left, which would put us out here at -6, then the function's value at that value of x is also going to be 9. Because that would be the symmetric point, wouldn't it? 3 units over, we're up at 9, so 3 units to the left, we have to be up at 9 to have the symmetric point. Let's find another point. Let's let x be -2. If we let x be -2, and we evaluate the function, -2, the square of that is 4, plus -12 plus 9. 9 and 4 is 13. 13 plus -12 is 1. So when x is -2, the function's value is 1. So that says when x is -2, the y value is 1. That's one point to the right of the axis of symmetry, one x value to the right of the axis of symmetry. So that means if we go one x value to the left of the axis of symmetry, the function's value there also has to be 1 to be the symmetric point. And now we can sketch the graph of this parabola.